In this video, we will learn about equations of equilibrium, 2 and 3/4 members, topics 5.3 and 5.4. Equations of equilibrium and 2 and 3/4 members. Objective is to apply equations of equilibrium to solve for unknowns and recognize 2/4 members. Three scalar equations, sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments about point O equal to 0 are the most commonly used equations of equilibrium in two dimensions. They are not the only equations, there are more than these three equations, but they are most commonly used. A rigid body is subjected to forces as shown. This body can be considered as a blank member. So we can see here that at point A there are three forces. Now by the algebraic addition of vectors for these three forces, we can resolve them to one single resultant force Fr. Similar to that, we can also resolve all these three forces into single resultant force at B. So Fr at B and Fr at A. So since this entire body is subjected to forces only at 2 points, this is called 2/4 member. The uniform truck ramp has a weight of 400 pounds. The ramp is pinned at A and is held in the position by the cables. How can we determine the forces acting at the pin A and the forces in the cable? So we have one unknown, like two unknowns here, AX, AY, and then tension in the cable G. How can we solve for these three unknowns using three support reactions? The answer is sum of forces equal to 0, sum of forces in y equal to 0, and sum of moments about point A equal to 0. So using this, we can solve for them. In fact, when we apply this equation, sum of moments about A equal to 0, then we do not need to consider AX and AY because they pass through A, and so they do not contribute for the moment. So applying this equation will help us to solve for, by the way, we also need to indicate the weight acting through G. So this is weight of the ramp, W. So using the sum of moments at A, we can consider the moment because of the weight about A and moment of tension about A, and that will give us the value of T. Okay, and once we get the value of T, we can apply sum of forces in x equal to 0. That will help us to solve for AX, and then sum of forces in y equal to 0 will help us to solve for AY. We will look at one example using these three equations of equilibrium. An 800-pound engine is supported by three chains, so 1, 2, and 3 chains, which are attached to the spreader bar of a hoist. So that's here, this is the spreader bar. You need to check to see if the braking strength of any one of the chain is going to be exceeded. How can we determine the forces acting in each of these chains? So we need to know what is tension force in chain A, chain B, and chain C. And why do we want to do that? Because we just want to make sure that these chains are safe enough that they can handle load because of the weight of the engine. Because if they are not strong enough to hold the 800-pound, 50-pound engine, then they will break. And when they break, you know that will cause an accident. So we have three unknowns, and we can solve them using three equations of equilibrium. So equations of equilibrium in two dimensions specifically are these three equations, where sum of moments about O can be any arbitrary point on the body. It doesn't have to be A, it can be any point as long as this object is in equilibrium, whether it's point B, C, or D. You can write this equation as sum of moments about B equals sum of moments about C equals 0, for example. These three equations are most commonly used equations for 2D equilibrium problems. There are more equations than these two, but we don't consider them for the course of statics. The solution to some of the equilibrium problems can be simplified if we recognize members that are subjected to forces only at 2 points. For example, at points A and B in the following figure. So this bracket here is subjected to one force at A and one force at B. If we rearrange this bracket, then we can see that the total force, like the force acting at A and B, they have the same magnitude but the opposite direction. That means number of unknowns are only 1 here, not 2. If we apply the equations of equilibrium to such a member, we can quickly determine that the resultant forces at A and B must be equal in magnitude and act in the opposite directions along the line joining points A and B. So let's look at a few more examples of two-force member. For example, this bracket here is two-force member. It has force at A and then it has force at B. The cylinder, hydraulic cylinder here in this machine is also a two-force member because it's being supported at 2 points only and forces are applied at those 2 points. So that helps us to reduce number of unknowns and solve the equations of equilibrium. So the problem solving steps for 2D equilibrium problems are, first step is define the coordinate system if it is not defined. Next, draw the free body diagram of the object under analysis. And third, apply 3 equations of equilibrium to solve for the unknowns. And those 3 equations are sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments about any point equal to 0. However, there are a few things that we need to note here. First thing is, if we have more number of unknowns than number of equations, that means we cannot solve the problem, and it's called indeterminate situation. The order in which we apply the equations of equilibrium, that matters, because if, for example, if we have 2 unknowns for vertical force and 1 unknown for horizontal force, then we should first solve for the horizontal force. We are not being restricted to use these equations in the order. We can use them in any order. Sum of the forces in x equals 0, sum of the forces in y equals 0, and sum of moments equal to 0. Those are our 3 equations of equilibrium. EOE, that's our acronym. You can use them in any order. It doesn't have to be like 1, 2, 3. If the answer of an unknown force comes out as negative number, then the sense of the unknown force is opposite to the assumed direction at the start of the problem. Say, for example, what it's trying to say is, let's go back and let's look at this example. So let's say we are solving for horizontal support reaction at AX, and we have assumed that AX will act in this direction. But when we solve the problem and we get the negative number for AX after applying this support, sum of the forces in x equal to 0, what it means that AX is actually going this way. So AX still acts here, but it will go in the opposite direction. Okay, so if we get the negative number for AX, otherwise if we get the positive number, that means our assumption for the direction is right. That's what being explained here, that if the answer is negative, then the actual direction is opposite to that of assumed direction.